Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO and OFDM wireless communication systems. So far what we have seen is we have seen how to model a wireless communication system, the bit error rate performance of a wireless communication system, what are the problems with the bit error rate performance, how to improve the bit error rate performance. We looked at the diversity using multiple antennas, receive diversity, and how receive diversity decreases the bit error rate. Now let us try to understand more about the wireless channel in a 3G, in a CDMA, MIMO, OFDM wireless communication system. So what we are going to do starting this module is to look at the wireless channel. That is, we want to ask the question, how does the wireless channel affect CDMA, MIMO, OFDM wireless communications? That is, how does the wireless channel, or basically the radio propagation medium, affect wireless, how does it affect wireless communication? Basically what we are looking to do is we are looking to characterize this wireless communication. We are looking to characterize the wireless channel. So what we are asking is, how does the radio channel, the propagation medium, affect the nature of CDMA, MIMO, OFDM wireless communication systems? For this we need to develop an in-depth characterization of the wireless channel. And let us briefly go back, let me refresh your memory regarding our wireless channel model. We said that we have a transmitter, let's call this a base station. So we have a base station and we have a mobile, and we said that there is a line of sight path for the signal to propagate between the base station and the mobile. So this is my mobile. However, if there are scatterers, such as for instance trees in my environment, then also there are several scatter paths. For instance, let us say there are buildings in my propagation environment. So these are some trees and some buildings, and therefore what I also have are, I have scatter paths. So I have a direct path, which is my LOS, or the line of sight path, and I also have several scatter paths which are my non-line of sight or NLOS path. So we have already defined this LOS equals the line of sight, or basically our straight line path, and NLOS is the non-line of sight or basically our scatter path. These arise from the scatterers in the wireless environment. So in the wireless communication channel is, as we have already seen, is a multipath propagation environment which arises because of the scatterers in the wireless environment. So there is a direct path or an LOS or a line of sight path between the transmitter and the receiver, but there are also several non-line of sight paths which are basically arising from the scatterers, that is the scattered signal components from the scatterers, such as the trees and buildings in the wireless environment. And we also saw that this wireless communication channel can be modeled as follows. So the channel impulse response of the wireless communication channel, again this is something that we have seen before, can be modeled as h of t equals I equals 0 to L minus 1 AI delta t minus tau I. So, this h of t, this is my wireless channel, this is the response of my wireless channel. This quantity, so we have L multipath component. So, the summation is I equal to 0 to L minus 1, which means L equals number of multipath components. I have AI, which is equal to the attenuation of the ith path. This we already seen. This is AI, which is the attenuation of ith path, and I have tau I, which is the delay of ith path. So, the channel impulse response is h of t equals summation I equal to 0 to L minus 1 A I delta t minus tau I, where L is the number of multipath components, A I is the attenuation of the ith multipath component, and tau I is the delay of the ith multipath component. Right? This is something that we have already seen before. Now, what we want to do is let us look at the same thing in terms of the power profile, that is the power profile phi of t can be defined as, well, this is defined as summation I equal to 0 to L minus 1 magnitude of AI square delta t minus tau I. So, this is magnitude of AI square. What is magnitude of AI square? This is the power of the ith multipath. This is the power, magnitude of AI square is the power of the ith multipath component. I can also write this as summation I equal to 0 to L minus 1 gi delta t minus tau I, where gi is defined as magnitude AI square, which is equal to the power, the ith component, or this is also the gain of the ith path. This also term can also be termed as the gain. Let me just write this clearly. This can also be termed as the gain this is also the gain of the ith path. So, the power profile is summation I equal to 0 to L minus 1 magnitude AI square delta t minus tau I, which is equal to summation I equal to 0 to L minus 1 gi delta t minus tau I. What this is saying is there is a power gi, or there is a gain gi, which is arriving at a delay of tau I, and gi is magnitude AI square. So, this gives the power profile of the wireless channel, right, which is the characterization of the arriving power with respect to the delay, that is tau. Okay. And now what we want to do is, for instance, let us take a simple example to understand this better. Consider an L equal to 4 consider an L equal to 4 multipath channel, that is, this multipath channel has L equal to 4 components, which means my h of t is given as summation I equal to 0 to L minus 1, which is 3 times g of I delta t minus tau I, which means there are a total of 4 multipath components. Let me write this as a table. So, I have the gain of the component, and I have the various delays, and this multipath power profile tells me that there is a gain G0 equals magnitude A naught square at delay tau naught. There is a gain G1 equals magnitude A1 square at tau 1. There is a gain G2 equals magnitude A2 square at tau 2, and there is a gain G3 equals magnitude A3 square at delay tau 3. And if I represent this schematically, if I draw a picture, let me now draw a picture for this example multipath power relay profile with 4 multipath components, it is going to look something like the following thing. I have a path which is arriving with gain G naught at delay tau naught. There is another gain G1 at delay tau 1. There is, let us say, another gain G2 at delay tau 2, and finally there is a gain G3 at delay tau 3. So, this is the multipath power profile, that is, this is the characterization of the power of the arriving signal component as a function of the delay tau, right, at various values of tau, what is the arriving power. And therefore, what we can, so therefore, this can be called, as we already noted, this is called as the multipath. This is my multipath power. This is the multipath power profile. This is my multipath power profile, and what you can see is that there are multiple components that are arriving over an interval of time. It is not a single component which is arriving as at a single instant of time, but there are multiple components arriving over a certain time interval or over a certain spread of time, and this spread of time is termed as the delay spread. So, if you look at this time interval, so first what you will observe is there is a spread of time. Spread of time means basically there is a duration of time, there is not a single instant of time, there is a duration of time or a spread of time. Or what you can also see is that the various delays are spread over an interval of time. So, the correct way to say this is the various delays are spread over an interval of time, and hence this spread of the delays, this duration or this interval of time over which these various signal components are arriving is also known as the delay spread. This is an important quantity for a wireless channel. This spread of delays, this is also termed as this quantity here, that is the spread over which these different signal components are arriving, these different multipath signal components are arriving, is also termed as the delay spread. Now, how do we characterize the delay spread of a wireless multipath channel? How to characterize the delay spread? That is the question that we want to ask and address right now. So, how do we characterize the delay spread? How to characterize the delay spread? Well, one way to characterize the delay spread is using a metric known as the maximum delay spread. One way is, so we have to develop metrics to characterize the delay spread. One of the metrics is the maximum delay spread, and that can be done as follows. For instance, let us say the first arriving component the delay corresponding to that is tau naught, and the last arriving component arrives at a delay of tau 1, then the maximum delay or arrives at a delay tau L minus 1, this is the last lth multipath component arrives at a delay tau L minus 1, then the maximum delay spread, which is termed as sigma tau max, or let me write it this way, sigma tau max is given as tau L minus 1 minus tau naught. So, it is the delay, it is the difference in the delay between the first arriving component and the last arriving component. So, this is the definition of the metric, one of the metrics to characterize the delay spread. This is termed as the maximum delay spread, which is equal to tau L minus 1 minus tau naught, that is the delay of the last arriving component minus the delay of the first arriving component, that is the delay of the L minus 1th path minus the delay of the 0th path, right. This is a very simple metric. Basically, it sees what is the last arriving component and what is the first arriving component, and what is the delay between, what is the difference in the delay, what is the time interval or what is the duration between these two components, and that is the duration over which the multipath signal is spread. So, this is known as the maximum delay spread. We have denoted this by sigma tau max. Okay. So, this is the maximum delay spread. For instance, again let us take a simple example. Let us go back to our L equal to 4 multipath channel. Consider a multipath channel with L equal to 4 components, and also let us say now that tau 0, that is the delay of the first arriving component, equals 0 microseconds, and tau 3, the delay, because L equal to 4, tau L minus 1 is tau 3, which is equal to 5 microsecond. Then what we are saying is that the delay spread, that is the sigma tau max quantity, that is the maximum delay spread, equals tau 3 minus tau 0 equals 5 minus 0 equals 5 microseconds, as simple as that. So, what we are saying is basically that in a scenario where the first multipath component is arriving at 0 microseconds, the last multipath component is arriving at 5 microseconds, the delay spread or the maximum delay spread is simply the difference between these delays, that is 5 minus 0, which is 5 microseconds. And to look at this pictorially, we can again just look at a simple picture to illustrate this point. I have different paths, gain 0, which is arriving at t0 equals 0 microseconds. Then I have a second path with gain 1, which is arriving at tau 1. I have another path with gain 2, which is arriving at tau 2, and finally I have my last path, which is arriving with gain 3 at tau 3 equals 5 microseconds. And now what you can see is that the maximum delay spread is the spread between the first and the last arriving paths. So, this is equal to 5 microseconds, that is my sigma tau max, which is the maximum delay spread, which is the delay between the first and last arriving component. So, that is the delay between the first and last arriving component, that is equal to 5 microsecond, which is the delay between the between the first and last arriving components. So, this is also my maximum this is also termed as the maximum delay spread. This is one of the metrics used to characterize the delay spread of the wireless channel. So, this is one of the metrics. This is not the only metric. We are going to look at another metric shortly. So, the maximum delay spread is one of the metrics and is a simple metric to characterize the delay spread of the wireless communication channel. It gives us an idea of the time duration or the spread of time over which the signal components are arriving. That is starting from the first time of arrival of the first component to the time of arrival of the last component, and the interval between them is the maximum delay spread. So, we will conclude this module here, and we will look at some other metrics for characterization of the delay spread in the subsequent modules. Thank you very much.